Hello everybody, welcome to a new IZ8 DWF repair video. I have just received this very nice and quite uncommon Commodore SFD-1001 floppy disk drive. And it even has a floppy disk inside, that's interesting. The case looks yellowed, but otherwise intact. This is an IEEE drive, originally intended for the PET computers. I've just removed the case screws because I wanted to have a quick look inside. And there is quite a lot of dust here. This is the only Commodore single floppy drive with two 6502 CPUs, as far as I know. And the electronic board has almost the same footprint of the entire case. It is interesting to give a quick glance to the floppy disk history. As always, all web pages I've used for my research are linked down in the description. According to the Wikipedia page, the first 8 inches floppy drive was introduced in 1971. However, as you can guess, 8 inches floppies are really a bit too large. You can see here the difference with respect to the 5¼ inch ones. And of course, the 8 inches disk drives were large and heavy too. So, for the expanding computer market of the late 70s, a smaller format was really needed, and in 1976, Sugar Associates introduced the first 5¼ inch drive, the SA400. And yes, that was a huge success. You can see a few sugared drives in both the Commodore disk drives for the PET line and on the Disk 2 drives for the Apple II line. However, both Commodore and Apple decided not to use the original sugared controller because it was really easy to come up with something more efficient and versatile in terms of disk capacity and reliability. The original 8 inches drives had a head positioning mechanism adequate for a track density of 48 tracks per inch, for a total of 77 tracks on one side of a floppy disk. A magnetic material with a 300 Hz coercivity value was used to get properly magnetized by the writing head as originally designed. The sugared SA400 drive was almost only a scaled-down version of an 8-inch drive. Track density was still 48 tracks per inch, and only 35 tracks would fit in the original 5¼ format. A bit later, the floppies were slightly modified to allow a total of 40 tracks. And also the magnetic material was just the same as the one used for the 8 inches floppies. In fact, it has the same 300 Hz coercivity value. Luckily, at this point, many other manufacturers started to make compatible drives, and others started to even introduce much better drives. In fact, according to the Wikipedia page, by 1979 there were new 5¼ inch drives that had a track density of 100 dpi. And according to this other page, probably the first 100 dpi drive was introduced by Micropolis. However, these new drives were not compatible with the older 48 dpi format. Magnetic media was the same, but the head couldn't be positioned over the larger and sparser tracks. Then we see that by the early 1980s, drive manufacturers started to make 96 tracks per inch drives. As you can guess, 48 times 2 is equal to 96, and so these new drives were able to reach correctly the older format tracks by double-stepping the head. However, these drives were introduced a bit too late. Commodore, for example, was already using the 100 dpi drives in their 8050 and 8250 dual-disk drives for the PET line of computers. We see in the schematics that they had 3 different choices for the actual 100 dpi mechanisms, each made by a different manufacturer, and none of them was made by Sugar. However, these early disk drives were still the full 8 type, just like the SA400. But not much later, Commodore wanted to make smaller drive units and even integrate them inside the newer PET machines, like this 8296D. Of course, they needed to remain compatible with the high-capacity 100 TPI format. At that point in history, however, the 100 TPI format was only used by very few computer lines, and so the half-8 compatible mechanisms were probably only manufactured by very few companies. As a matter of fact, on all the half-8 100 TPI drives made by Commodore, we find only the JU-570-2 mechanisms made by Panasonic. After removing all screws and unplugging all connectors, we can lift the electronic PCB. This board has quite a few wire connections. I wonder if it's an early revision. However, this drive was never opened before. Now I can remove the chassis from the bottom case. And we must unplug the case LED connector, paying attention to the wire color orientation. At this point I could wash the plastic case with soap and remove all the dust with the help of some brushes. After washing, I can let the case dry outside. Notice how the top part has yellowed and the bottom part instead shows the original color. This drive power supply has a big mains transformer plus low voltage rectifiers with big smoothing capacitors and linear regulators. To avoid excessive heat dissipation, it's important to wire the transformer for the correct mains voltage, that in Europe used to be 220 volts in the 1980s, but is now 230 volts, and most of the time as high as 240 volts where I live. So for this drive we must connect this black wire in place of this red wire. So I've just removed the original insulating sleeve, soldered the black wire adding a new heat shrink stabbing and insulate the exposed end of the red wire. Of course we must check that the 5V rail has no issues, and it looks okay. And the 12V rail has the correct voltage too. These Panasonic drives, however, have all the same problem, leaking electrolytic capacitors. As you can see in the picture, the corroded area looks quite bad in this particular drive. Here is another corroded spot. I've serviced other drives of the same type in the past, and all had leaking capacitors. So the first thing to do is remove the spindle rotor. I've marked the position of the 3 screws and 1 motor hole to be able to reassemble it in the exact position. This is probably overkill, but it doesn't hurt anyway. After lifting the rotor, make sure you don't displace or lose the spacers on the motor shaft. Then we need to remove 4 more screws from the motor PCB. Notice that one screw is slightly different and must be placed in its original position when assembling back the drive. Before lifting the PCB, we need to unsolder these 2 pins. They are connected to this flat cable, which is way too short and would easily break if we attempt to lift the PCB. At this point, we can separate the PCB from the drive and start working on it. All the small electrolytic capacitors must be removed. Most of them are dead anyway. Keep a list with values and position to replace them with the correct type. These 3 capacitors instead are usually good. They show no leakage and no excessive ESR. So far it was never necessary to change them on all drives I've serviced, but you may want to check their ESR value. Be aware that they are non-polarized electrolytic ones. I then clean the whole PCB with plenty of isopropyl alcohol and the aid of some Q-tips. The damaged areas must be sanded to remove all corroded copper. In this spot I can already see that I'll need to add some wire to restore the broken trace. This other spot instead doesn't need much effort, just some thinning of the exposed copper or a new layer of enamel after soldering the replacement capacitor. Here I also needed to lift some other component pins to have a flat area for the copper sanding. Most of the lifted solder joints needed to be reflowed anyway, because the Ultina alloy was corroded too. The sanding is almost done here. It doesn't seem that we have broken traces. Now, whenever I can use different kind of capacitors in place of the electrolytic ones, I usually do. In this case, the two 470 nanofarad electrolytics can be substituted with film capacitors of the same value that are not much taller than the original ones. All the others will be substituted with regular electrolytics, not the super small ones that I personally don't trust too much. Of course, I need to mount them horizontally to allow the PCB to retain its small vertical clearance. Notice that in this case I have added insulation on one capacitor pin to avoid shorting the pins together. This one can be mounted horizontally without any particular precaution. This is the only problematic area, but with some care all can be bent down enough. Here I have jumpered the interrupted trace with a copper strip. This was the most problematic spot. All joints have been soldered with the help of liberal amounts of liquid flux. This also helps in avoiding shorting adjacent traces. However, be sure to check for possible shorts with the multimeter. Before reassembling the drive, I will reconnect the flat cable that was unsoldered from the motor PCB. This is powering the infrared LED of the index sensor, and this sensor is not connected on the Commodore electronic board because they used a different method to identify the sectors. So in theory I could even leave it disconnected, but in reality I know I'm going to need the index sensor during the final checks of this drive. For this reason I've soldered two pieces of wire in place of the original connector. Notice the red wire goes on the side next to that other infrared LED in the white cylinder that's part of the right protect sensor. Then I soldered the black wire to the smaller trays on the flat cable. Of course, first I've removed some of the plastic cover with a sharp knife. And the red wire goes to the larger trays, of course after exposing a portion of the copper under the plastic material. Then I added a drop of epoxy glue to completely insulate the solder joints and add mechanical stability. This kind of flat cable is very fragile and would break easily. Usually I leave the epoxy curing overnight. Now it's time to reassemble the spindle motor. The added wire must be routed in the lateral space and must not push against the PCB. Then we make sure the spindle can be rotated freely without friction. The PCB must not be pushed up by any of its parts or wires. However, I didn't do my homework correctly, since the magnetic assembly cannot rotate freely because the PCB is pushing against it. So, after removing the PCB again and making sure the added wires were not pushing one side up anymore, the motor can now freely rotate. So I can finally replace all the screws. Yes, it looks fine. To access the heads, we need to remove this metallic cover. It was held in place by 2 screws. Now I can access both the magnetic heads and the carriage rails. I can clean the top and bottom heads with a cotton swab with a few drops of isopropyl alcohol. Just like this. Then we must verify that the head carriage can move back and forth without too much friction or bending. We can remove any dust and grease deposits from the rails with, again, the cotton swab and more isopropyl alcohol. By the way, always move the head acting on the carriage rail supports, never touch the upper parts. I have assembled the electronic board on the chassis and connected the drive, but left it outside the chassis. Let's power on. Well, good sign. 2 flashes, then LED permanently off. And the other LED is solid green. Excellent. Let's power cycle. Yes, the same 2 flashes, then solid green. So far so good. And a quick test connecting my pet shows that we can read the error channel without issues. So I'm trying my luck at formatting a disk. It's advancing track by track. This longer pause was a clock zone change, but then it advances again. Another zone change now. But wow, looks really good so far. Last zone change. And this took forever, but is now advancing again. And OK, step to the meter to write the PAM and directory, and green LED, wow! And yes, I could load the directory. Notice the unbelievable amount of free sector that this drive is capable of squeezing inside a regular dual-density floppy disk. Also saving a small basic program worked with no issues. I am impressed. The wires in position 21 and 22 on connector P1 are coming from the index sensor, so I removed them temporarily. And let's measure in diode mode with the multimeter. At power off we have no continuity. But when we apply power, the sensor is activated because there is no floppy inside now. So, to get the index pulse when a floppy is rotating, I've connected the orange wire to ground and the red wire to plus 5 volts through a 10 kΩ resistor. The scope probe will be placed on the red wire. The pulse is clearly visible on the scope. And the timing is already almost correct at 201 milliseconds. However, it's better to bring it as close as possible to 200 milliseconds. The spindle speed can be adjusted by turning the small trimmer through the hole indicated in this picture. Yes, that's good enough now. I'll show an easier but less precise method later in this video. First, I'll try with CBM link to copy the floppy I found inside this drive. And wow, all blocks could be read fine. It seems it was a kind of financial program from 1988, but the disk content is in German language and I don't understand a word of it. Then I've written a copy of the test and demo disk for this drive. However, the blocks free count is wrong, so let's fix it. The validate command completed, so let's see. Yes, now not all blocks are reported as free. And as promised, let's check the spindle speed in an easier way. We can use the 8296D diagnostic program. Now we press D and then 0 for the single drive. Of course, the speed deviation is already 0 now. So it's all for this video. I hope it was interesting and that you learned something. If you have any question, please use the comment section below. Have a nice time and thank you for watching.